So let's go over Chapter 11, Section 1, which is measuring motion. So today our key ideas are: what is motion? What is the difference between velocity and speed? And how can you use graphs to show the motion of an object? What is motion? Objects move in many ways. Cars travel in straight lines along busy roads. Satellites travel in circles around Earth. Motion is so common that it probably seems very simple. However, in science, we must be careful to define motion precisely. Imagine sitting in a moving car with your eyes closed. If you could not see the road moving by the car, it would be hard to tell the car was moving. Motion must be defined relative to other objects. The objects used to define motion are called a frame of reference. In physics, any object can be a frame of reference. The object that makes up the frame of reference are treated as if they are moving. All right, so that little check means that we're going to have a reference check. So, define what is a frame of reference. So we're going to define that right here. It is objects used to define motion. Okay, let's see if I can. All right, great. Okay, let's go on. Okay, in this multiple exposure photograph, the trees and ski jump provide a frame of reference for the motion of the snowboarder. You can tell the snowboarder's movement because of the position relative to the trees is changing. All right, so we're going to come back up here. In the science, motion is the change in position of an object relative to a frame of reference. In the image shown below, trees provide a frame of reference for the motion of the snowboarder. Okay, when we describe motion, we are often interested in how far an object has moved. Scientists describe how far an object has moved using two terms, distance and displacement. So let's come up here, looking closer. Give another example of a frame of reference for a motion for the snowboarder. So we are going to write in here possibly the ramp, the snow, or the ground. Okay. Distance and displacement. You are probably familiar with what distance means. Distance is how far an object moves. If you run one lap around a soccer field, you have run a distance of about 350 meters. In contrast, displacement is a measure of how far the starting point is from the ending point. If you run 7 laps around a soccer field and end up exactly where you started, your displacement is 0 meters. So it seems as if you haven't moved, but you have. In many cases, displacement is shorter than distance. Okay. 3. Which is longer, the runner's distance traveled or displacement? It is distance. Okay. When you describe distance and displacement, you need to give both a length and a direction. You can describe the direction of displacement by using cardinal directions such as north, south, east, or west. You can also describe the direction relative to a reference point. For example, in the figure above, the direction of the student's displacement could be described as away from the goal. How are speed and velocity different? In everyday language, we often use the words speed and velocity as if they mean the same thing. However, in science, speed is different from velocity. You know from experience that some objects travel faster than others. A running horse travels faster than a jogger. A race car travels faster than a running horse. Speed describes how far an object travels in a certain amount of time. In other words, it describes how fast an object can move. In contrast, velocity describes both how fast an object is moving and in what direction it is moving. As when you describe displacement, you can describe the direction of motion using the words such as up, down, left, and right. Okay, applying concepts. A scientist records the motion of an object in a notebook. She writes down that the object moved 10 meters in 3 seconds. Did the scientist record a speed or a velocity? Explain your answer. So, she described a speed. Described a speed because the scientist did not specify the direction. The direction. She must have written down speed instead of velocity. So we know that it is velocity because she did not give a direction. Now, if she would have said she went 10 meters east or left in 3 seconds, that would be velocity. Okay. Okay, so let's look at number 5. Could you determine the velocity of these objects from the information in the graph? So we have the graph here. We have 7.3, 19 meters per second, and 96 meters per second. So we have the graph here. Could we tell the velocities? No, we could not, because the graph does not show the direction. Okay, so because it doesn't tell us the direction, we do not know the velocity, we only know the speed. Okay, adding velocities. Imagine a person sitting on a bus. The bus is traveling east at 15 meters per second relative to the street. The person gets up and walks towards the back of the bus at 1 meter per second. How can you determine the person's velocity relative to the street? That's important, to the street. Before the person starts walking, her velocity is the same as the bus, which is 15 meters per second east relative to the street. However, when she is walking toward the back of the bus, her velocity decreases. You can use positive and negative numbers to figure out the person's velocity when she is walking on the bus. First, you would have to define which direction is positive motion. In this case, you can define positive motion as the motion eastward. Therefore, the bus and everyone on it has a velocity of plus 15 meters per second. The person walking toward the back of the bus is moving in the opposite direction from the bus. Therefore, she has a negative velocity. Her velocity is negative 1 meter per second. To determine her total velocity, add the two velocities together. Her total velocity is plus 15 meters per second plus a negative 1 meter per second, which gives her a positive 14 meters per second. Since we have defined positive motion as the motion eastward, the person is moving 14 meters per second east. Okay, critical thinking. Suppose you define positive motion as a motion westward. What would the person's total velocity be? Okay, so it will be the opposite direction. So it would actually be a negative 14 meters per second or 14 meters per second going in the east direction. Okay. How can we calculate speed? Remember that speed describes the distance or object travels in a certain amount of time. Therefore, to calculate speed, you need to measure two quantities, the distance traveled and the time it took. The SI unit for speed is meters per second. Okay, here's our reading check. What two quantities do you need to know to calculate speed? We need to know the distance traveled and time. Okay. Average speed. Most objects do not travel at one constant speed. Instead, their speed changes from one instant to another. In this case, it is often used to describe the average speed of the object. Average speed is the total distance traveled by the total time it took to travel that distance. The equation below describes the relationship. Speed equals distance divided by time. V equals distance divided by time. Let's look at the example. A sledder moves 132 meters down a hill in 18 seconds. What is the average speed of the sledder? Okay, so let's look at this. So we list the given and unknown. Given is 132 meters and time is 18 seconds. We do not know the average speed. Write down the equation. Speed equals distance divided by time, or V equals d over t. Insert the known ones. We know that 132 meters divided by 18 seconds equals the speed of 7.3 meters per second. All right, let's look at what we can infer. Is it often easier to calculate the average speed of an object than to calculate speed at each point along this path? What do you think? The reason for this is, okay, so to calculate the speed, the speed of an object at every point, you must know the distance and time at each point. However, to calculate average speed, you need to know only the total distance and the total time. So that is why it's easier to calculate the average speed instead of the point at each point. So the sledder has an average speed of 7.3 meters per second. The sledder's speed may have changed many times as he moved down the hill. At some point, he may have been traveling faster than 7.3 meters per second. At other points, he may have been moving more slowly. Instantaneous speed. The instantaneous speed of an object is its speed at a given instance or a point in time. Because we cannot divide by 0, we cannot use the equation for speed to calculate instantaneous speed. However, tools like the speedometers in cars can measure instantaneous speed. If an object is moving at a constant speed, its instantaneous speed is equal to its constant speed. This is the reading check. Why can't you use the speed equation to calculate instantaneous speed? Because you can't divide by 0. Okay? How do we calculate velocity? Remember that velocity is the speed of an object in a particular direction. To calculate the velocity of an object, you must first find the speed of the object. Then you must indicate the direction. That's more direction of the speed. Let's look, for example, for several days in 1936, Alaska's Black Rapids Glacier moved at 89 meters per day down the valley. What is the velocity of the glacier in meters per second? So what is known? Distance 89 meters, time is 1 day, and direction is down the valley. So we can find velocity. So 1 day equals 24 hours. 1 hour equals 60 minutes. So we got it to 86,400 seconds. So to find velocity, our distance is 89 meters over 86,400 seconds, which we get 100,000 meters per second down the valley. So the glacier moved at a velocity of 0.0010 meters per second down the valley. Notice that the symbol for velocity, V, is the same as the symbol for speed. You can use the speed equation to calculate the velocity. Just remember to include a direction when you describe an object's velocity. A swimmer swims 110 meters toward the shore in 72 seconds. What is the swimmer's velocity in meters per second? Okay, so we're going to take 110 meters and we're going to divide it by seconds, and we are going to get 1.5 meters per second toward the shore. It is important we write toward the shore because that's what gives us velocity. Okay, this is the end of part 1. I will do a second part 2 for motion.